supposed to, in this problem it says sketch the graph of the function by applying the leading coefficient test, by finding the zeros of the polynomial and plotting sufficient solution points and drawing a continuous curve through the point. Well, we can calculate points by hand or we can calculate points with a calculator. Hey, how about the calculator? You want to do it by hand? Okay. All right, so one thing I'm going to do is let me go ahead and put this in my calculator. We'll take a minute to do that. Let me turn this off. Okay, so now let's think about the leading coefficient test. The leading coefficient test says if I got an even exponent like I've got here, if I'm thinking about my graph, we'll just kind of, I'm going to draw a graph to sketch here, okay? Usually if I had an even coefficient, even exponent like the fourth power I had here, no matter if I put a positive or negative number in it, wouldn't it go up at both ends, just thinking about a fourth degree? Whether I plugged in a negative or a positive, it would go up. But what about this negative in front of it? What's that going to do to your sign? I would have had a positive, let's take it one thing at a time. If I put negative 100 in there and I said I'm going to raise it to the fourth power, I'd have a really large positive number. But then when I put the negative in front of it, that's there, this negative right here, isn't that mean it's going to go down instead of up now? It's going to switch that positive to a negative. And wouldn't it work the same way on the positive end? Right? If I put 100 in there and raised it to the fourth power, I'd have a really large positive number. But the minute I put that negative in front of it, it's going to mean I'm going to get just as large of a negative number, right? So those yellow arrows are kind of me thinking on here. The black arrows are where I'm going to kind of sketch the graph. So that's all we had to do with the leading coefficient test. It's just kind of analyze the exponent and is there a number in front of it or here there's a negative 1 in front of it. They just write the negative. Now the other thing I need to do is look at the zeros. And again, we're going to try to do as much of this algebraically as possible. Couldn't I, if I want to look at that and solve it, I could set y equals 0 because I'm going to solve it. That would help me find my x-intercepts. What could I factor out of that to help me maybe look at this a little easier? Do I want to factor with a negative out front? No, okay. Let's pull that negative out. X to the fourth plus 9x squared minus 20. That's a little easier to look at. Do you remember, and this has been a while, I know since you factored, since you had geometry last year, but when you have this x to the fourth and this x squared right here, we can factor this as if it were a quadratic equation. We can just say, okay, instead of having, normally when I factor this, if it had just been x squareds and stuff, for instance, I would have said, okay, I would have had an x here and here, right, if it had just been x squared plus 9x minus 20. But because there's an x to the fourth and an x squared, do you remember that all I have to do to adjust that is just to put an x squared here and here instead of just an x? And I can see that if I multiply that out, that's going to work. Sometimes you would do something like this in the Algebra 2 book. They would say, let u equal x squared. Then I would rewrite the equation as negative u squared plus 9u minus 20, and you'd factor it all out just like it was a normal little factoring problem too here. Okay, so I could factor it like this and then go back and change those u's to x squareds, or I can just put the x squareds in and forget about the u's. You know, it's just a mental trick you're trying to do if your brain doesn't like looking at those x squares. What do you multiply that gives you 20 and at the same time adds up to a negative 9 now? 4 and 5, and they would have to be both negatives, wouldn't they? So negative 4 times negative 5 would give me this positive 20, and negative 4 plus negative 5 would give me that negative 9 there. Okay, am I done factoring yet? Can I do something else here? Yeah, we still got the negative out front. We got the difference of two squares, x minus 2, x plus 2. And now, honestly, I could look at the second one now as a difference of two squares, or I could do this. What about this x squared minus 5? If I want to get it broken down to what we call a linear term, I could set it equal to 0. And I could move the 5 to the other side and just square root both sides. That's how we've been looking at it. And when I square root both sides, right? And when I square root, what do I have to remember to write on that 5? Plus and a minus, because there are two different things that would give me 5 if I squared them. If you look at this, if I write these as factors, how you write these as factors is you would say that's x. Remember, a factor is x minus the number that you actually get when you solve for the 0, right? So it would be x minus square root of 5 and x minus minus square root of 5, but that x minus minus square root of 5 would become a x plus square root of 5, yep. So could I have factored this? When I start seeing numbers that aren't perfect squares, could I start doing this? That's just x minus square root of 5, x plus square root of 5. You could, couldn't you? You could go down here and do all this down here. You start seeing that if it's something that's not a perfect square, we still could have treated it as a difference of two squares, or we could come down here, work it out like this, and then go write it up there. So you're getting in this section a lot of things that are irrational factors like this, where you get these square roots now, and you're not used to seeing them so much. But they're zeros too, aren't they? They're solutions too. We don't like them because they don't look like whole numbers, and they sure aren't very easy to graph, are they? But those are zeros. So let's go, those are part of our graph, aren't they? So let's go do this. Okay, we know we have zeros now. Wouldn't this one, let me write the zeros in green just so they stick out. If I said x minus 2 equal to 0, wouldn't I get x equal 2 as a solution, right? This one would give me x equal negative 2, right? If I said x minus square root of 5 equal to 0, wouldn't x equal square root of 5? And what would I get for x plus square root of 5 if I set it equal to 0? It would be like a negative square root of 5, right? I'm just out of room on the iPad, so I'm going to kind of verbally say that instead of trying to cram it on here and making a bigger mess than I have to. So those are zeros. Let me go graph them. 2 and negative 2 are easy. But we're going to have to know, well, what is square root of 5? So let me go back to my home screen and square root 5. That's about 2.2. So at 2.2, which is really close in there, and at negative 2.2, which is going to be really close in here. As a matter of fact, I probably got it way too far over just because this thing is big and the iPad takes a little dot from it. We can kind of sketch this now. We got enough information because we know where our x-intercepts are, and we know what direction the graph's going because we use that leading coefficient test. The thing about it is, do I really know how high? I know I'm going to start low and I'm going to go through that 0, but do I really know how high up in the y's this is going with anything that I've got right now? I could kind of put something on here, but it might not be very accurate, right? So what let me go to my table of values now and get some good points. I can even take you can hit graph and look at the graph just to see what it looks like. Oh, well, that's interesting. Are there ever going to be any positive values here if you look at your graph? So what we could do, it looks like if we wanted some good points here, maybe we know these directions of these two black arrows are showing us where the graph is, but let's go to the table and get something that we could graph that might be a little nicer looking. How about, what do you think?
5.
Okay. 5, negative 420, not going to work so well. Nothing on here is going to work so well from what I have here. The closest thing that it looks like would be at 1. It's at negative 12, and at negative 1 it's at negative 12. So 1, negative 12 is going to be way down here. I'm just going to put it as far down as I can get. Negative 1, negative 12. I might want something on the other side, though, so let's see. At negative 3, it's at negative 20, so it's even further down than those two dots that I tried to cram on there, isn't it? So maybe I just do something like this, given what I've got to work with here. Come on. This is actually going up, and it's bouncing down just a little bit and going back up. Let's see if you can see that on your graph. You really can't even tell it on the calculator, can you? You would think there was just 2 zeros to this if you were looking at this calculator. If you're looking at a regular window, it just looks like, something like that. But it's actually doing a little dip and coming back up there. How do I know that? The intermediate value theorem says if it's at 0 and then it goes to 0 again, there had to be something else in there, right, in between them. So it's doing this little tiny dip that's not even showing up on the calculator. It's coming down here. It's going to go off the screen, come back up. And hopefully yours, you've got more room to play with, hopefully on paper. It's going to come here, it's going to do another little dip and come back up. and then it's going to go down. And I want to show the down part with my arrows on the end of my graph, which is what these little black arrows here that I had were, right? That was where I was using that leading coefficient test, right here and right here. If I wanted to better picture this on my graphing calculator, I could change my window, but I kind of see what I need to do here, so instead of playing around with the calculator just because I could, we're just going to say, okay, we know it's going to do some little minute dip there that's not even noticeable as far as what accuracy we're graphing at. We can't even see it on our graphing calculator, but we can at least show it on this graph so that somebody else might realize it's there.